Hey everybody. Today we're talking about the logit function, which is hugely useful when modeling a phenomenon that has exactly two possible outcomes, so a so-called binary response variable. Here's the official definition. When p is the probability of some event, the logit of p is the log odds of that event. Typically we use a natural log, although that doesn't matter too much. That's what I've written here. ln of p divided by 1 minus p. I have a whole video on odds and odds ratios. I'll throw a link to that up top. The main point of the logit function is that while probabilities run from 0 to 1, logits run from negative infinity to positive infinity. Here's a picture of that. You can see as probabilities go from 0 to 1, the logits increase from negative infinity all the way up to positive infinity. Also notice that when p is 0.5, so even odds, the logit is exactly 0. It's not surprising that the logit function is sometimes also called the log odds function. That's just what it literally does. Transforming probabilities with a logit function makes them more reasonable candidates for regression. I think an example makes this really clear. The chances of being accepted into a university generally increase with a student's high school grade point average, which in the US at least typically run from 0 to 4. Acceptance rates at a certain university for different GPAs are shown in this plot. And here I've incremented grade point average from 2 to 4 in increments of 0.1. And we see the acceptance rates generally increase, going from just a little more than 0 to almost 100%. And you can see a sort of characteristic S shape. That'll show up a lot of times when you're modeling a binary response variable, so essentially getting proportions of successes and failures, in terms of a quantitative explainer. Now, it's not a good idea to just fit a linear model to this. And there's at least two reasons for that. First of all, if you look at the ends, you can see that this regression line is dipping below 0 and over 1. So we're predicting ridiculous acceptance rates at the extreme ends of this plot. Negative proportions of success over 100%. Secondly, and possibly more importantly, this line is just a bad fit for the data. It doesn't capture the real shape of this data at all. Remember, we have this really distinctive S shape here. And if you look towards the center of this plot, you'll see just a little bit to the left of center, the dots are almost entirely below the line, and to the right of center, they're almost entirely above the line. So we're just not capturing the true trend in the data. On the other hand, if we take the logits of the acceptance rates and plot those against GPA, now we do have a very linear shape, and it makes perfect sense to fit a line to this. And this is the idea that's going to form the basis of logistic regression. Because the logit function is continuous and monotonic increasing, it has an inverse. And on the right here, I've written the formula for the inverse, which comes up all the time, again, in logistic regression and elsewhere. The inverse logit of x is given by e to the x over 1 plus e to the x. Here's a plot of that. It's not a coincidence that it looks like a cumulative distribution function for a probability function. The inverse logit function transforms log odds into probabilities in the same way that the logit function transforms probabilities into log odds. One last fact that's sometimes useful both for computation and for interpretation of logits. The difference between the logits of two probabilities is the log of their odds ratio. Here's the math behind that, super fast. On the left-hand side, I've got the difference in the logits. On the right-hand side, I've just put in the definition of logit. Next, I apply a log rule. The difference of two logs is the log of the quotient. And then I just observe that the inside of that logarithm is the odds ratio. The difference between the logits of two probabilities is the log of their odds ratio.